Okay, thank you, Mr. Chairman, for the presentation. As it was mentioned, the title of my talk is related to the magnetic properties of carbon nanotube-based nanocomposites. It means carbon nanotubes with embedded magnetic nanoparticles. The work has been done in close collaboration of my group in Belarusian State University of Informatics and Radio Electronics and group of Professor Javier Tejada from Barcelona. Also, National Research Nuclear University MEFI was involved in this project. Here is the outline. After short introduction about magnetic anisotropy and relaxation of the magnetic moment, I will pass to the samples, how do we fabricate them. Then I will show experimental results related to metastable states with various relaxation times, how we use the law of the approach to magnetic saturation to elaborate our data and to extract the correlation function of the local magnetic anisotropy axis. And finally, we'll pass to the main result of the work, temperature dependence of the magnetic viscosity, which was extracted from the experimental data, and how do we explain this unusual dependence that we obtained, and we will talk about the function of the nanoparticle size distribution. And finally, I will conclude my talk. So in this conference, we have heard a series of talks related to magnetic nanocomposites. Even now, we followed a very interesting talk about how it is possible to produce magnetic nanoparticles. It was plenary talk dedicated to magnetic nanocomposites. And one of the most important thing among any others is the magnetic anisotropy, which in principle is determined by many other contributions like magnetic crystallinity, shape anisotropy, magnetic elasticity, surface, which is especially important for fine nanoparticles. And we have not forgot about dipole-dipole interaction between nanoparticles, which can smash the contribution of other anisotropies. For example, here I show you the result of AFM and AMFM studies of closely packed nanoparticles on a surface of silicon. Packing density was around 10 power 10 over centimeter square, and we see the formation in MFM image. We see the formation of blocks, and magnetic and nanoparticles are, from the magnetic point of view, are indistinguishable here. But if here is the same density, packing density, and we were able to grow array of carbon nanotubes, each of them contained only one nanoparticle. So it's chemical vapor deposition, but not from flying catalyst, but from fixed catalyst on the substrate. In this case, the stress was increased, and MFM image showed us that we deal with magnetically isolated nanoparticles. That happens because we change the magnetic elasticity of the nanoparticle when they are unstrained and free on the surface. We see the strong in-plane anisotropy, while after they were embedding inside carbon nanotubes, we see the signature, strong signature of the perpendicular anisotropy, and micromagnetic simulations confirm this fact. So the main goal of our work was to find the answer on the following question: does anisotropy affect the relaxation of the magnetic moment? So I'm sorry for this naive picture, but just to remind you how magnetization and relaxation occurs in solids. If we deal with bulk, we apply external magnetic field much greater than the saturation field, and we have the homogeneous distribution, the homogeneous magnetization. As soon as we switch off the external field, first initial fast domain distribution with opposite magnetization occurs, and then domain walls start to be pinned, and we pass through, we arrive to the critical state, and the slow magnetization begins, and it passes through various metastable states. This rate of slow relaxation is strongly dependent to the many parameters like microstructure, magnetic properties, and so on. So by studying the relaxation magnetization, it is possible in principle to extract very useful information. Hopefully, the time of this slow relaxation from the experimental point of view is detectable. But in magnetic nanocomposite, if we deal with magnetically isolated nanoparticles, here by red line I just mentioned the easy axis, and when we applied the great external field, we magnetize it to saturation magnetization. After switching off, we have various processes of slow relaxation, and after some long period of time, it should be this picture. So each local magnetic moment should be oriented along the easy axis of magnetization. And in experiment, usually the magnetization versus time is measured. It is well described by this simple equation, where it is necessary to introduce this parameter S, which is magnetic viscosity, and T naught is the inverse of the damped frequency. So by fitting this experimental data in semi-logarithmic plot, it is possible to extract to evaluate the viscosity at various temperatures. So about samples, as I told, we work with carbon nanotubes, so we consider it as a magnetic nanocomposite. Why? Because the catalytic particles to growth carbon nanotubes usually are 3D metals. In our case, we use ferrocene, which contains iron, the solution of ferrocene in xylene. So this is the source of our catalytic nanoparticles. The method is atmospheric pressure CVD. So we inject in the reactor this solution and heat, and under some condition it is possible to grow on the silicon substrate, for example, the oriented massive of carbon nanotubes. This is seen image of this sample. So we use also the concentration of ferrocene 10%, which is close to its maximum solubility in xylene. In this case, it is well known from literature and also from our experiments. As it is seen from backscattering electron image, here the brine spots are iron-based nanoparticles. Why iron-based, I will tell later. So they are distributed all over the sample. For such high concentrations, iron-based nanoparticles are embedded inside carbon nanotubes, inside walls of carbon nanotubes, and also outside walls of carbon nanotubes. But in any case, they always are covered by carbon shells. By this method, we produce multi-wall carbon nanotubes. And this is very important because it protects from the oxidation. These carbon shells protect from the oxidation, and we have very stable properties. After that, we remove. Yes, these brine spots are heavy metal. Mm-hmm. Yes, thank you. Thank you. Then we destroy this carpet and make a powder which consists of blocks. Each block contains oriented massive of carbon nanotubes, but between them blocks are disoriented. The diameter of iron-based nanoparticle or ferromagnetic nanoparticle is determined by the diameter of the CNT. Under conditions we use, the diameter is within this range, 20-40 nanometers, and we may estimate the single domain size for iron and cementite. This is our two main materials. According to Kondorsky, and this critical size is in the range of 25-30 nanometers. So we believe that we deal with single domain nanoparticles. Here you may see the example of carbon nanotube extracted from this massive, and black spots are these embedded iron-based material or nanoparticles. From X-ray diffraction, we concluded that the main phase is cementite with small inclusions of iron and also graphite. So this is typical XRD picture. Then from magnetization versus temperature, we also get the confirmation of the presence of these two phases. Blue curve is for 10% of ferrocene. And we observe two Curie temperatures. One is related to cementite and another to iron. Measuring magnetic hysteresis loops, it is possible to obtain the coercivity versus temperature and arrive to the blocking temperature, which was from this data was estimated by us as 131 K, which fortunately is less than Curie temperature of cementite, so everything is good. By fitting HC versus temperature within this equation, we found the exponent zeta, which in our case corresponds to 0.77 in perfect agreement with the random orientation model of the local magnetic moments according to work of Pfeiffer and Schuppel. I remind you that for parallel magnetic moments, as Ben Livingstone obtained many years ago, this exponent should be 0.5. 0.5 does not fit our data. So from field-cooled and zero field-cooled magnetization measurements, we obtained important results that, for example, data measured at 100 Ersted, we got a small change in magnetization at ferro-cooled measurements. It means that ferromagnetic nanoparticles are strongly coupled, mainly, we believe, by the exchange interaction. The maximum in the zero field cooled curve at 100 Ersted was not reached. This is in agreement with the value of the blocking temperature. Measurements were done up to 300 K. At higher measurement field, 1 kilo Ersted, we obtain a large distribution, two main peaks, and they could be fitted by two various curves. It means that at least we have two volumes or two maximum around which our volumes, for example, are distributed. So metastable states could be associated with arbitrary orientation of the axis of local magnetic anisotropy, and also by Hay distribution of anisotropic barriers. So from M versus H and field-cooled, zero field-cooled measurements, we conclude that the system is characterized by strong H coupling and by random magnetic anisotropy. These are two necessary conditions for application of the random anisotropy model. The random anisotropy model tells us that the saturation approach, that the magnetization approaches saturation according to this simple expression, where parameter or exponent alpha depends on the dimensionality of the sample. In our case, we expect three-dimensional case, and in this for three-dimensionality, exponent alpha should be minus 0.5, which was perfectly confirmed by fitting the experimental data within this simple equation. To go further or deeper, it is necessary to apply a more complicated expression proposed many years ago by Eugene Chudnovsky and extract the correlation function of the magnetic anisotropy axis in the real space. So the task was to fit the experimental data by this equation, where C is the correlation function. And applying the inverse Laplace transformation, we obtained that the result, experimental result, open circles could be well fitted by the random anisotropy model if we use such expression for the correlation function, where J is the Bessel function of the first kind and R naught is the characteristic size of the radius of the nanoparticle. From that we extracted the exchange field, like slightly less than 3 kilohertz and random anisotropy field slightly greater than 5 kilohertz. So anisotropy dominates. And here is the obtained correlation function. It oscillates. The same, I would like to say that the same shape of the correlation function was recently obtained for skyrmions, for example, in the work of Chudnovsky and Garanin, also with oscillations from plus to minus, which means the reverse of the magnetic anisotropy axis. So now I pass to magnetic relaxation data. Here you may see some examples of M versus time. You see range of time is minutes, hopefully. From elaborating this data, it is possible to plot viscosity versus temperature. This is our result in the temperature range 75 and 300 K. Below I don't show because there was problem with the sensitivity of the squid in this case. First of all, it's necessary to pay attention on the non-linearity of this dependence. While in literature, usually S versus T is linear. So the task was, this non-linearity is related to the distribution of volumes. And the task was to find this distribution function of the volume of ferromagnetic nanoparticles. So the model is as follows. Within the slow relaxation model, and the necessary condition for this magnetic field is much smaller than anisotropy field, and our anisotropy field is 5 kilohertz, so we are well below. Applying result from this book, nice book, S is viscosity is expressed by this equation. We may, first of all, we obtain that it was not possible to fit the experimental data if we use a usual expression for the distribution function without this phi versus theta, simply 1 over v exponent minus v over v naught. So it was necessary to introduce by hands some test function, temperature dependent test function. At the moment we don't know anything about it, but this helps us to fit the experimental data. And this phi is related to the temperature dependent anisotropy. So the task was to solve this transcendental equation for phi, and by substituting from random anisotropy model expression for the anisotropy constant, it is possible to arrive to this equation, S times logarithm this relation, T over T naught is equal to some function f, temperature dependent exponent minus f, where f is a product of some constant gamma naught, phi test function, and gamma. Gamma includes temperature dependence of the of the coercivity and of the saturation magnetization. B is the block temperature. So here are our main results. So by this expression, it was possible to fit the temperature dependence of the viscosity. Here is simple F versus temperature. We catch only low temperature part, but it was not possible to fit high temperature part. And finally, this test function, which in the first approximation was obtained as a polynomial of the second degree. So we see that in some range it's temperature independent, constant in temperature, and then start to grow. What does it mean?
You have 5 minutes more.
Yes, I am to be conclude.
Okay.
So thank you. In this temperature range, 75-150 K, our phi is constant. It means that the viscosity, which depends on temperature in this temperature range, is determined mainly by gamma, temperature dependence of the viscosity, which is inverse proportional to K square, anisotropy energy square. So that means that the increase in the viscosity with temperature in this temperature range is determined mainly by the decrease of the magnetic anisotropy energy with temperature. So the relaxation processes, important conclusion, the relaxation processes are determined by the magnetic anisotropy in this temperature range. When we pass to higher temperatures, phi is not constant, is temperature dependent, and S start to be determined mainly by this test function. So it means that the role of the anisotropy decreases with temperature, and the relaxation processes are determined mainly by thermal fluctuations, as in principle it should be. In this plot, I show the distribution function, F versus volume, for various temperatures. We have some, so we see that the F does not depend, or almost does not depend on temperature. Only for 300 K we have some deviations. This is probably due to the fact that we approach the blocking temperature and we are going out of the conditions of the slow relaxation model. If we apply this test function, this usual function, distribution function, dashed line, we see that it goes outside the range of the distribution function, which includes the test function. And here is the same result in the 3D plot. So the main conclusions. First of all, a ferromagnetic nanocomposite based on carbon nanotubes has been synthesized. Ferromagnetic nanoparticles are iron-based, mainly cementite with some inclusions of iron. We measured magnetic hysteresis loops, zero field, cool curves, magnetization versus temperature, and we determined the mechanism of interparticle interaction and the distribution of particles by volume. And for the first time, data on magnetic relaxation were analyzed, taking into account the contribution of temperature-dependent magnetic anisotropy. Thank you very much for your attention.
Thank you for your talk. You have shown a very nice order of the carbon nanotubes on top of the substrate. It is possible to change the properties, for instance, applying a magnetic field or something when you are preparing this carbon nanotube.
Excuse me. During synthesis?
Yeah.
Yes, it is possible because we influence on the catalytic nanoparticles which are ferromagnetic. But we, in our lab, we cannot do it. We have no such possibility. Actually, the CVD process is, from the first glance, is very simple. You inject something, you put substrate, and then after half an hour you see, oh, we have the sample. But there are a lot of controllable and sometimes uncontrollable parameters, especially during such simple system as atmospheric pressure CVD. So the reproducibility of such samples is a state of the art, more the state of the art than the state of the science. So you need some technician which has a great experience in this
Thank you.
issue.
Thank you.
Nevertheless, this idea is very nice. We should think. Thank you very much.
I have a question. When you say viscosity, what do you mean by viscosity? Because is it something related with the magnetic relaxation?
Yes, because I'm going to this equation. This parameter arises in m versus t. For t is time. So how fast? So here we magnetize and then switch off the field, magnetic field. Actually, in real experiment, usually we apply not 0 but some minus 50 stat in order to overcome the remanence of squid insert, for example. Nevertheless, 0, and then magnetization by itself start to go to 0. And how it goes, not linearly, but via this viscosity. And in this viscosity, there are anisotropy, barriers, interactions, and so many parameters. So it's some macroscopically introduced parameter, which is from one point of view could not give us precise microscopic view. From the other point of view, on the other hand, it could give us good idea about some mechanisms. So that is why we introduce distribution function. And in this distribution function, which is called volume distribution, in fact, there are not only volume, but also some physical properties. But always is gathered into one parameter, volume.
Okay, thank you very much.